Peter Medawar is not the first to have tackled the phenomenon of aging in the framework of evolutionary biology. See the module on Weismann. However, he has set the question in its contemporary terms, namely, what is the origin and evolution of what is commonly spoken of as aging? More specifically, the question is, how can natural selection explain the appearance of the decline in vitality of individuals with age, and especially its progressive and not brutal character, given that 1. This decline occurs after reproductive age and therefore cannot constitute a trait preserved by natural selection. 2. The onset of post-reproductive age is itself part of the decline in vitality and therefore cannot have been retained for its benefits by natural selection. Before Medawar, Weismann had proposed a solution that Medawar dismisses. According to Weismann, natural selection eliminates older individuals because they are less competitive in reproduction. To be fair, Weismann proposes a relevant distinction between two forms of senescence. One does not depend on exposure to the environment. Medawar calls it innate senescence, while the other consists in the accumulation of injuries. Medawar calls it environmental senescence. The distinction parallels the distinction of two factors of death in the tradition of the study of Gompertzian curves of mortality, intrinsic and extrinsic. See the module on Gompertz. Weismann correctly presupposes that in any satisfactory explanation of the apparition of aging, environmental senescence should explain why innate senescence appeared in evolution, and not the other way round. Yet Medawar reproaches Weismann with confusing the accumulation of lifetime with the decline of vitality. This difference is indeed crucial and has become classical. Medawar calls aging, or mere aging, the simple accumulation of lifetime independently of the increase in vulnerability with age. Dorian Gray, he says, is an example of an individual aging in this sense alone. Medawar calls senescence a decline in vitality including faculties, sensitivities, and body energies that accompanies mere aging. The terms have been used in that sense for a long time in evolutionary biology. But under the pressure of cellular and molecular biology, evolutionary biologists have more or less dropped the term senescence and used the term aging in that sense. To get back to Weismann, he believes that environmental senescence and the absence of perfect repair mechanisms is the explanatory fact, while Medawar gives it a role simply of reinforcement in the appearance of innate senescence, and explains the appearance of innate senescence without relying on environmental senescence. Let's see how it does that. Let us first assume a potentially immortal population, that is, one that ages without being senescent, or whose vulnerability does not increase with age. Each generation would gradually lose its members by accident and renew them by young individuals. Medawar nicely represents this idea by introducing the metaphor of a stock of 1,000 test tubes that are randomly broken and replaced at the rate of 10% a month. This figure represent the number of individuals for each age group in months, for a total duration of the experiment of 20 months. Total of test tubes after 20 months is, of course, still 1,000 test tubes. In this hypothesis, the gradual disappearance of an age group in an immortal population is mainly due to the deadly hazards of life. Indeed, in the wild, fatal accidents most often prevent populations from aging. In contrast, in the new biological age for humanity that has recently appeared, this is no longer the case, and this constitutes the major source of evidence for us of the existence of senescence. This hypothetical setup has a first major consequence. The mere passing of time is indeed sufficient to explain an increase in the probability of having died, and therefore a decrease in the number of individuals of a given generation. In turn, this decrease entails a decrease in the force of natural selection. In other terms, traits that appear later in life do not play an important role in the reproductive value of this age group because the individuals that reach such an age are too few to bear on the frequency of traits in future generations. Their contribution to evolution is low. Medawar thus states that the force of natural selection weakens with increasing age, even in a theoretically immortal population. By immortal here, we must, of course, understand potentially immortal. Medawar's idea relies on Fisher's theoretical calculation of a stratification according to age of Malthus' power growth equation. According to Fisher, the reproductive value, generally called V of x, is dependent only on the survival rate, therefore on age itself, or mere aging in Medawar's terms. Medawar explicitly says that in a non-aging population, each test tube may lay claim to an equal share of the ancestry of future generations, and its reproductive value is invariant with its age. But that the older the age group, the smaller is its overall reproductive value. To understand that, let's get back to the figure. The smaller a group of individuals, the smaller its contribution to the pool of genes in the next generation. In Fisher's terms, the reproductive value V of x is proportional to the survival rate L of x. We do not want to presuppose here a decline in fertility with age, because this is precisely a part of what we want to explain. Now, suppose that these potentially immortal test tubes reproduce themselves and are subjected to genetic mutations. Suppose that some mutation appears, which has abruptly deleterious effects, occurring late in life, say 5 years. These mutations would occur in individuals who are already fewer in number because they are older. Natural selection could hardly eliminate them. On the contrary, if these deleterious effects occurred early in the life of test tubes, say at the age of 1 month, the consequences would be catastrophic, and these mutations could and certainly would be eliminated by natural selection. Now, if the mutations had effects 1 year after birth, there would be an impact, but the most important part of the reproductive contribution would already have been made. Indeed, the reproductive value V of x is already very low when x reaches a certain age. Relative to the contribution of the whole population to the next generation, a late deleterious effect is therefore negligible. In summary, favorable and unfavorable variations appear at different ages in the test tubes. The later they appear, the weaker the force of natural selection. Again, as Medawar says, the force of natural selection weakens with increasing age. Medawar's great idea is that this is sufficient to explain the apparition of innate senescence. How does this work? Suppose the random occurrence of mutations with deleterious effects. Indeed, natural selection largely eliminates those that have an early detrimental effect, because they affect numerous individuals at an age whose reproductive value is high. But will it be less efficient on traits that have a late effect because fewer individuals are concerned? Additionally, pleiotropic mutations that appear in a potentially immortal population are likely to be eliminated. Pleiotropic traits are traits with multiple effects. In this context, a favorable effect early in life and an unfavorable effect later in life. The reason is that in Medawar's terms, a relatively small advantage conferred early in an individual's life may outweigh a catastrophic disadvantage that appears only later. In Fisher's terms, we could say that a pleiotropic trait increases reproductive value, V of x, at age x, and decreases reproductive value, V of x plus n, at age x plus n. If in the test tube population there was one population with a reproductive rate of 10% and another one with a rate of 11%, that would yet decay after 2 years, say. The second population would prevail over the first one. This leads to what we could call Medawar's theorem of a self-enhancing senescence. If hereditary factors reach their patent expression at an intermediate age of life, if the age of patent expression is variable, and if these variations are themselves heritable, then natural selection will act to reinforce the delay in the age of expression of those factors that are unfavorable, and as a consequence, to squeeze the effects of those that are favorable. A recession and precession, respectively, of the age effects variable of genes. A special case of this general theorem is the apparition of a post-reproductive phase in some species. This trait seems paradoxical because reproductive value would abruptly reach zero at some age. However, such a trait will not be eliminated by natural selection, for the same reasons as explained. However, it would automatically secure a part of life that would be a dustbin for the effects of deleterious genes. In other terms, all deleterious genes with late effects would be able to accumulate. This is generally the reason why each such gene reinforces the self-enhancing effect of the accumulation of traits of aging. They do not tend to appear earlier and earlier. They just tend to make the transition between traits that are subjected to natural selection and traits that are not more abrupt. Therefore, just as Weismann assumed, environmental senescence is sufficient to explain the apparition of innate senescence. Innate senescence, however, is not the result of natural selection, as Weismann thought. Medawar shows that it is rather a byproduct of evolution, a sum of transmitted traits that just cannot be eliminated, although they can be very deleterious. In conclusion, senescence, whatever its form, plays a negligible role in evolution because natural selection repels its effects. The accumulation of senescence processes at a late age is a phenomenon produced by exclusion through natural selection and is self-sustaining. The evolution of innate senescence is the result of, first, the inability of natural selection to counteract the low pressure of repetitive mutation when mutant genes make their effect apparent at ages when the vast majority of the members of a population do not actually reach 2. The fact that the delay in the time of action of a deleterious gene is equivalent to a delay in the time of the onset of senescence. And 3. The fact that natural selection may in fact reinforce such delay and conversely accelerate the age of onset of patent action of favorable genes. The third factor is the most significant.